happy to be here. So anyway, my name is Rob Hawthorne. This is Bart Bergquist. And just kind of a quick, just so you know where we're going, I'm going to do a quick introduction, talk about kind of where the project started, what the program was, and the goals for the project. We'll run through the design, just architectural and the kind of passive house design. Look at the different assemblies of the building, and then start looking at some of the construction details, especially of the building envelope, because that's really the critical part here. Look at a few photos, talk about the products and systems that were selected for the house, and then kind of go wherever you guys want to go at the end. So my name is Rob Hawthorne, as I said. My background is in architecture. I practiced at a larger firm here in Portland for about 5 years. And then I went off on my own, and I kind of went into the architecture field, but then I realized that in order to get projects that I was really interested in, which was high-performance buildings and kind of infill housing projects, things like that, that it was real hard to get your foot in the door, especially with the economy the way it was in 2009. So I figured the best way to do that would be to be my own client. And so I started PDX Living as a design build firm doing development projects, and got my general contractor's license, and then found this guy. But I'm also LEED accredited and a certified passive house consultant.
So mostly I am. I'm the blood and guts of the side. I'm the guy who, I've done this work I've been building for 30 years. My family I grew up doing construction, so one of the things that I've always been trying to do is move on to doing higher efficiency homes, because I just see the need for it. I see how poorly houses were built, and so this is a place where Rob and I came to the meeting, and we enjoyed each other's ideas about this, so we started trying to move towards building the more efficient homes. Then he discovered Passive House just as we were designing or finishing up the design on the first house we did, and so we were pretty close already. It didn't take much to go to the Passive House, so this is our second Passive House project. So that's where I've been.
So a quick background, I basically told you why PDX Living was founded. But basically it was to design and build affordable, highly efficient, environmentally responsible, modern homes. The first project that Bart just mentioned was the core house, and that was, should we turn off lights? Would that help? Yeah. Okay. Nope. Is there another switch? Is that better? Okay. The first project was the core house, which is over in Northeast Portland. This was built as a spec house, meaning for sale, and it was the first passive house in Portland, and as far as I know, the first spec passive house in the country. We started it. When did we start? Basically the beginning of 2010, and finished and sold it in October of 2010.
Yeah, tear down was in December.
09.
09, yeah. Freezing. Yes, it was cold.
But it was a really fun project, because we spent quite a bit of time. We took our time building it and really spent a lot of time just looking at each detail as we actually did the construction, not having done, in particular, a passive house before, but also not having worked together before. We just kind of felt our way through it. But it was a really fun project, and the person that bought it has basically turned into our biggest proponent. So that's been neat to see. All right, now moving on to the Trekhaus. Ella and Randy, who were the clients in this project, just by chance came across the core house and really liked it, and started looking into passive house and realized that was the way they wanted to go. They moved to Portland a couple of years ago and knew they wanted to live in a high efficiency house. Really, their goal was net zero energy. So they did a ton of research seeing what was out there. And they liked the idea of the core house, and so they asked if we would be interested in working with them. And they found this piece of land over on Southeast Taylor and 43rd. that seemed to work well. So we started designing, and the program that they had is the lot was zoned for 2 units, and so to them it made sense. Go ahead, build the full 2 units, gives them kind of a passive income as they get older. They're looking for a 3-bedroom, 2-bath unit. One of the requirements was that there's an office on the first floor, kind of right near the entry, because Randy is a chiropractor, so he wanted to be able to practice out of his home without having people go all the way through the house. As I said, their goal is to reach net zero energy use, and that means 100% electric. You can't really offset natural gas use. So we basically decided from the get-go not to have fossil fuels in the house. A big thing for them was also the garden. They really wanted to have an urban garden that they could grow a lot of their own fruits and vegetables. So that had an impact on the site design. And then things like quality, contemporary. They kind of like the contemporary look that's in the city. Simple forms and systems, mostly to keep costs at a reasonable level. And then something that's, I'd say, more one of our requirements was conventional construction practices. There's 100 ways to skin a cat, but we figured the best way is to do it in a way that's not going to scare each subcontractor that gets to the on-site, because that's just going to make costs go up. So we're really looking for ways of doing things that people have seen before, but we just take it to the next level in terms of efficiency. And then for construction, they had budgeted about $485,000 for the 2 units. So just real quick, I don't know if you guys how much of this you've seen already, but on the left here we have the first floor. I didn't do a site plan. I have an aerial view coming up, but this is, north is up, so south, and then also the street are down here at the bottom. On the first floor, so the 2 units, this is 1 unit here, entryway, and because of that office on the first floor, which is right here, we decided to move the living areas up to the second floor. That helped, one, because you get kind of more dramatic spaces with the sloped roof, and you're not confined to, in this case, an 8-foot ceiling, and then also just opening up to the street, but still providing privacy. But you can see there's a bedroom/office on the in the front here, another bedroom in the back, and then we have bathroom here, and a laundry. And then they didn't really need a garage, but they did want a place for bikes and for storage and that sort of thing. So we put a kind of garage replacement, or we're calling it the workshop, in the back of the property there. These are the stairs going up. So moving up to the second floor, we just have a big kind of loft-like dining, living, kitchen area, and then 1 bedroom and a bathroom. Oops, too far. Okay, so then this area that just got hatched is just to really emphasize I was talking about doing simple forms and shapes. And that's really a big deal in a passive house, because one of the big factors in a passive house is your surface area. So if you can minimize that by having an efficient shape, that's to your advantage. And then also another reason is for the construction details and to eliminate thermal bridging. Intersections are always difficult. So if you can really keep the shape of the building as simple as possible, that helps. So what's hatched here, the hatch is the passive house envelope. So for example, the workshop isn't conditioned. We have just a little, there's a heater in there to make sure it doesn't freeze, but the idea is to keep it essentially at ambient temperature. So this wall here between the two is our fully insulated wall. And then there's a few things, so that we don't just have a box. We designed on kind of some decorative features on the box that also provide program elements. So, for example, up on the second floor, there's the decks here that are. We'll show some details, but they're not structurally connected to the main building. And then there's this, we call it the bump out here, which is on the first floor and the second floor. On the first floor, we have part of the above ground cistern for a rainwater collection system and the pumps and all that. And then on the second floor, that's where the heat recovery ventilator goes.
One of the things that you might see in another slide is as we're building this, the first thing we do is get to what's called the heated envelope or the airtight envelope. So a lot of like the back walls for the shop, since even though they were on the first floor, we didn't build the back walls. We just suspended them up with a couple of posts. This front porch or front mechanical area, that wasn't built until after we got our air seal. So you have to think about the steps a little bit differently when you construct this way. It adds a little cost, but it also allows you to get your air seal easier.
So here's a aerial SketchUp view of the project. Just a couple things to note. You can see this is the street down here. And in this case, we pushed the house back as essentially almost as far as we could to the north. And the reason for that was for the garden space that they want to have here. They just wanted the southern exposure. Then you can see where this is the living area here up on the second floor, and the deck's kind of overlooking that. Then there's something else. Oh, the roof. That was something that we had a lot of discussion about what the shape of the roof would be. And we were limited in the height to, I think, 30 feet. So it was we need to have enough room for the solar panels, but at the same time we couldn't go so high that we obviously were above the zoning requirements. So we ended up doing what essentially is a flat roof. It's a low slope roof, and it actually slopes opposite of what you would ideally want it to. It actually slopes toward the north. The reason for that was if you're in the living space, that's where we wanted to have the extra height and kind of open up toward the views. So it didn't really make sense to slope down in the direction that you want to be opening up to. And then we also, when you're doing a flat roof, they actually work really well. They're really good roofs. The main problem is when you have penetrations through those roofs. That's where, a lot of times you hear about leaking roofs, and they're usually, a lot of times that's flat ones. But if you can eliminate penetrations, then, and use the right product, you really have one of the best roofs that you can do. And so we came up with this plan to, one, eliminate every single penetration that we could. So we have one penetration through each roof, but it's actually just through the little bump out, so it's not even part of the conditioned envelope. It's the plumbing. We had to have one plumbing vent go through. And then the other way that we eliminate penetrations is with a PV installation. Usually, you put in PVs and you end up with hundreds of penetrations because they all have to be connected to the structural part of your building. But in this case, so we told them you can't do that, and the only thing that you can do is connect to the parapet on the outside of the building. That's the little wall that sticks up above the roof, and then also in the middle of the building. So we worked with the solar contractor to come up with a system that would span that. It's really something that apparently hasn't really been done before. And most people looked at that and said, no thanks, we're not interested. But actually we just got the system for one of the houses installed yesterday, I guess, right?
Yep.
Okay, so this is a screenshot from the Passivehouse planning package. This basically just tells you whether or not you meet the criteria for Passivehouse. Have you guys seen this before? Is this? No? Okay. So actually, you can see part of it here. The PHPP, it's called Passivehouse Planning Package. It's an Excel file that was developed by the Passivehouse Institute in Germany. But it's a massive Excel file, and you can see some of the tabs here. I mean, there's pages for basically every single detail of the building. But it all comes down to this page. This is whether or not you meet the performance. When Matt Groves was here, did he talk about what the requirements were for Passivehouse? You guys remember those? Good. All right, so real quick, the one requirement is the specific space heat demand. So that's basically over the course of a year, how much heat is required per square foot to keep the house at 68 degrees is what they set the comfort level is. The limiting factor is 4.75 kilobTUs per square foot per year. So you can see with the design, ended up about 3.9. We just want to have a little bit of buffer in there in case something during construction came up where we ended up with a thermal bridge or something, just gave us a safety factor there. Then there's the pressurization test. Did Matt talk about blower doors? Does that kind of make sense what that means? Okay. So blower door test has to result in a 0.6 air changes per hour. And we tested at, I think that's right, 0.34. It was right around there. So again, it's kind of giving us a safety factor. Just the hope is that over time, if something loosens up, building shifts a little bit, that we're still within the requirement for passive house. So that's something that we'll be wanting to do as, maybe in a year or two, is just come back and see what the tightness of the house still is. And then the third requirement is the specific primary energy demand. Did Matt explain that? Maybe? Okay, so real quick, I won't go into too much, but basically what Passive House is interested in, and this is really unique just to Passive House, as far as I know, no other green building standard does this, but that's the number for the total energy use of the house per square foot, but they don't measure that at your meter. The idea is that you measure that energy use at the point of energy production. So they estimate that to get power from the power plant to your house in Portland, and the number they use is just kind of an average for the country, but you lose, let's see, something like 60% of your energy just through transmission. So there's a multiplication factor. It's basically what the house is expected to use times, I think it's 2.7. I have to look to see exactly. But that's the number that they're looking for. And the idea for that is if your true goal is to go to net or carbon net zero, not just energy net zero, is that you really have to offset your total use at the source. Because if your power plant, here, fortunately, we have hydropower. It's less of an issue, but most of the country is really coal. So the idea is that you have to offset what is being produced at the power plant, not what is going through your meter. And so the idea of Passive House is that you get your actual usage as absolutely low as possible before you start introducing things like PVs and renewable. So anyway, it's an interesting topic. But then there's a few other things here that we won't really talk about, but there is a little bit on the, let's see, that's the heating load. There's the cooling load. And then there's a frequency of overheating. The reason you don't see a percentage here is that this project has mini-split heat pumps that provide cooling. So if those are used, there's not going to be any overheating. But if you actually model it without those heat pumps, we predict something like it's just under a 2% overheating, which means over 77 degrees is how they calculate that. So anyway. Moving on, just looking at, that was kind of what was predicted. Ella and Randy moved into their unit, it was just before Christmas, right?
Yeah, just before Christmas.
So they have 3 months of energy bills. So we're interested to see how that went. But what they saw is that January, they ended up with using about 12.7 kilowatt hours per day. And then February went down to 11.7, and then their most recent one was 10.3. Those numbers, it obviously makes sense as we get into warmer weather and they're using their heating system less, and their water heater, which is a heat pump water heater, is getting more efficient. So we're seeing that dropping. But if you take, just because we want to jump ahead and see where things are going, if you look at their average for those 3 months, they're using 11.6 kilowatt hours a day. Again, hopefully that goes down over the year, but if you multiply that times 365, you end up using 4,324 kilowatt hours per year per unit. If you go back to the Passive House, our model showed 4,385. So, hopefully their numbers go down, but we're looking pretty good so far. And then the PV system that they just put on here, you can see the photo from yesterday, has a predicted output of 4,581 kW per year. So it looks like we're, at least so far, doing pretty good for reaching their goal of site net zero energy. Okay, moving into some of the assembly details. I'll do this and then we can go to the next one. and I don't know how many people are going to fall asleep here, but anyway, this is a little diagram of the typical floor assembly for the first floor. If you start down at the bottom, we have our compacted gravel. And this here is supposed to represent our perlite. Do you want to explain the perlite?
Sure.
We can pass this around.
Have you guys do you guys know much about or heard about perlite? Perlite is a obsidian. It's a baked obsidian. So obsidian, the first when they crush it, this is about the amount they crush it to. Then they send it through 1400 degrees. And every molecule of, or surrounding all the molecules of water is obsidian. So when it gets heated, liquefies, and then just like popcorn, the steam blows it up. So they have two products. One is the structural, but this is a smaller porous. This is your agricultural stuff. This isn't really what we use because this crushes really easy. This stuff they use in all sorts of different constructions. They pour it into. This is what they fill all of your what do they call it? CMU buildings with for insulation. So that goes in as part of the construction. We used it. It comes in. Did we show bags of it yet?
Yeah, not yet. We'll get there.
Okay. So that's what the perlite is created with. And the next layer that is our EPS, 4 inches of EPS. In between those two layers is the yellow layer is a vapor barrier. So we use a 15 mil vapor barrier.
I'll take this.
No, you keep going. I'll turn this around. This is the vapor barrier. Comes in sheets.
And we'll have some photos of all this here, so it'll make sense. So just real quick, the reason for the perlite is, one, we like that it's mined in Eastern Oregon and it's produced in North Portland. So it's kind of a local product, which is kind of cool. And then it's also a non-petroleum based product, which we like. So it was kind of an experiment. Not many people have used perlite in this application, but I figured we'd give it a shot. But yeah, it was a little cheaper. So it was an interesting process. So that's to the vapor barrier. Then we have another 4 inches of insulation directly below a 4-inch slab, and we actually use the slab as a finished product on the first floor. Okay, typical wall assembly. So kind of going back to trying to use our standard construction. Basically, it's a standard stud wall. To get some extra insulation, we upsize the framing members from 2x6 is pretty typical to 2x8. But then we did advanced framing, which essentially means you eliminate any piece of wood in there that doesn't have a purpose, which probably percentage-wise on a typical project is, yeah, it's a substantial amount of wood that really doesn't have to be there if you really look at what it's doing. So I think we have some photos of that. And then the cavity in here we used a blown-in cellulose insulation, which is a recycled newspaper. And then there's the sheathing, this plywood, and that's our air barrier. So as we go look at photos, you'll see that that's essentially where we're trying to keep the air. That's the barrier to keep that building airtight. Outside of that, we have 4 inches of polyisobutadiene insulation, which has a foil face. But then we use 1x4s to create an airspace behind the siding that basically just gives somewhere for any water that does get past the siding. It gets into that airspace and drains behind there. And then there's the siding, and we use mostly fiber cement, but we have a few places with wood and some other materials. Sorry, let me back up. I didn't mention slab on grade. We have R value of R38. Walls are R49. And then the roof, which we end up with R77. It's basically, again, pretty typical assembly up to here, which this is our sheetrock. We had 11 and 7/8 inch TJIs, which they're basically manufactured kind of trusses, but they're anyway, they look like that. I-beams, yeah, thanks. And then we have our roof sheathing, plywood. Again, that's where our air barrier was. And then 7 inches of polyiso on top of that. And then the single ply roofing, which we don't have, but it's basically a really thick piece of
60 mil fiber type.
Yeah. Do you want to talk about these, or?
So the first thing we found on the last job was that we had a real problem with a thermal bridge at the concrete, where our two concretes met. So the first job we did, do you guys know, I mean, how many of you have seen the details on construction and stuff like this? I mean, so somewhat familiar. Most construction, you would put your slab down inside the concrete. That's standard operation. But the problem is, by putting your slab down by your concrete, you have a thermal bridge right here at the heel of all of your walls. So what we did was we actually built the exterior walls, put a piece of plywood in here, an 8-inch piece of plywood, and then poured our slab inside the walls. It's more of a commercial operation. It causes some problems with my concrete guy. He really didn't like me for that, but it gave us the ability to get our insulation down to where it's closer to the insulated barrier below. Also, we have so you can see the insulation outside and inside, and then the sheet and then concrete. And so one of the things that you have to really pay attention to, and everything you do in Passive House, and what everybody should be doing is in construction, is paying attention to where the air barrier is. Most of your air, you guys all know, most of your heat in conventional building just goes out through attrition, through air. So what we do is we pay real attention before we even start is where we're going to put all this. So this is our vapor barrier, the vapor barrier is 15 mil plastic that goes underneath, and then we glue it up the side of the wall. So it's a way of creating a continuous barrier from underneath and up.
And the plywood there continues the air barrier.
Yeah, and then the plywood continues, so we glue it to the plywood and tape the top and go on up. So
we also did, this here, I'll pass this around, but this is a gasket that we got out somewhere in Massachusetts or something like that. But this went right under here, under the sill plate, just to create another kind of safety barrier for air. So we use these in a number of places.
A couple of things that we don't do, a lot of people use what they call sill, which goes a piece of foam, about an 1/8-inch foam that goes on top of all the concrete, and you set your walls on top. It's a barrier for bugs. It's also a barrier for moisture transmission from the concrete to the wood. We don't need that because we have a continuous vapor barrier of going all the way out, so it's a replacement, and then we put the gasket on. So there's a few things that are standard in operation and standard in construction details that we don't end up having to do because we do with this. These are the bags of the perlite, and they came in basically a 2 or 4 square, I can't remember. I think they're 4 square per bag, and we just left them in the bags because one of the things we found out real quick that is if you open them up, this stuff just flows everywhere, and it is also a water attractant, so it will suck up water like you cannot believe. And we did this in the middle of March, and it was just pouring. So we just laid them in and packed them in very tightly, and then we started rolling out our vapor barrier. The vapor barrier is, I think, 20 feet. It's like 20 feet wide. What?
10 or 12.
No, it's wider than that. It's like it rolls out. Anyway, so say it's wide. So then wherever the vapor barrier connects, we tape it together, and then we create around each of the penetrations, for the plumbing penetrations through here, you have to create a boot around it, and you, because when you lay this out, you can't really get it perfect, so you lay it out as best you can, then you boot around all those, and booting just getting very tight to the pipes, because we don't want the moisture. One, we don't want any vapors coming from the gravel up into the building, and we want to keep all the air from going out of the building.
Very good. You can also see that at this point we had already framed the first 4 walls.
Yeah, and this is the plywood. This is a marine plywood that we put all the way around it, 8 inches tall.
The slab is going to go to the top of that marine plywood. You can see certain things, and there's a single top plate. Usually there's 2 pieces of top plate, so we eliminated one that really isn't necessary. And then the spacing of the studs is 24-inch on center instead of 16 is pretty common.
The other thing you'll notice is if you look above all the windows, there's no headers. So we eliminate all headers. We eliminate anything that we can move into. When you're building a second floor, actually when you build anything, you've got rim joists all the way around the building anyway, which is a structural member. And I still haven't gotten most of my engineers to explain to me why you have to have a massive piece of lumber over your header if you've got one above that. So our engineer just wherever he wants so if there's a larger than, I think it's 5-foot opening, you have to go with a double rim. So there's a lot of waste in the construction just because that's the way we've always done it. And I mean, I've done that. I've been framing. I was taught framing 25 years ago, so I know the standards. And this has been kind of fun because I get to break the rules. It's a lot of fun. So this is the beginning. So now we've framed the front wall that we had left off, and then you can see where we've taped up. We've glued up and then taped on the vapor barrier underneath, and then this is all of our taping coming up over the top. And one of the tapes we used is we were going around the building. We used a 3M, which is a single piece. If you're gutsy, you can peel a little bit back and then see how really sticky that stuff is. And it's got a very good stretch. So one of the problems you have with when you're doing this kind of construction, you want to make sure you've got a lot of room to stretch, because that material is your air barrier, and it's got to survive a lot of dumb construction. So this is our barrier at the. Okay, this is a wall section, isn't it? Is this the wall? Oh, this is the roof. Wall to roof. So pretty much the way we did it is we tried to build straight up to the top of the wall, and instead of a lot of times what you do is you build your wall to the roof line, and then you put your joists out here, which causes some problems with thermal bridging, and also harder to get your corners made. So we build our walls straight up to the tall point of the wall of the roof, and then we plywood all the way around, and that allows us to keep our. Did you do your? Yeah. So that keeps our vapor barrier. Again, we've traced our line around, so it's on the outside of the plywood, underneath the final insulation barrier.
And just to kind of contrast that with typical construction, usually you can see we had like a 5-foot overhang on the front, I think it was. Mm-hmm. And normally what people would do is they take the roof structure and just cantilever that out if they wanted to have a big overhang. But that intersection there, it's basically impossible to air seal and impossible to get a continuous layer of insulation around. Mm-hmm. So the idea with what we did, and you'll see this in some more photos, is that we were building a box. You can see here, this is our box. Then we take this box and we get it completely air sealed, and then we make sure that we can essentially continuously insulate it as well. And then we move on and add all the decoration to it.
So now you can see all the white tape is the 3M, and then we learned on the last job, and then we finally decided we weren't going to do this again on the next job. We used a Vicor tape, and Vicor tape is really good on like plastic to plastic, or areas that are really that are not wood. But if you want to stick it to wood, it takes a primer. So you got to prime the wood and then put it on. So it's a 2-part. So it's much more labor intensive. It's half the price of the other stuff, but it's and it also has a petroleum product. So on this project here, around these windows, where we had to come up around the edge of the window, if it's far enough out, we're finding it's bleeding into the paint. So it's making our nice white paint turn black. not fun. So we're going to move to all the 3M type tapes. So learning process. This is our sucker door. This is an invention that we created just so we could find the holes.
So I think Matt talked a little bit about blower door, which essentially is where you put a fan on the building that measures the amount of air that's going through so you can see how much leakage is in the building.
This takes that to about 500% above that. So these are two 3,000 CFM fans pointed outward, creating a negative pressure in the building. And what we found was, one, I just wanted to do it really, really bad. Sounded like fun, but what it told us is that instead of having to do smoke pencils, which is really hard to find all the holes and everything, we could walk around. Once we put the pressure on the building, you can actually walk around the outside of the building, and every hole screaming. It's whistling at you. So you just walk around and listen for them and plug them, and pretty soon the exterior of the building becomes quiet. So it's really, it was just fun in the first place, but now it actually has a purpose. So
we time this so we do it after we've made our box, but before we've had any subs or anything come. But it's the best opportunity to check and see if there's problems with our airtight layer. So actually we don't have it from this project, but
do they have speakers here?
We'll find out. But just to kind of give you an idea, this is from the core house. Let's see what happened here. How much pressure we're talking about here. I don't know, do we know if there's speakers?
Oh, it doesn't matter. You don't need speakers on this one.
So you can just kind of get an idea of from this video.
So the door didn't exist. So we've got the it doesn't seem like much now, but Rob decided to say, well, pull the thing off.
So the fans are running out. You can see it stuck to the building, but I see.
And there's nothing else holding this but air.
So it's a lot of pressure. I mean, you can't open the doors when the fans are running or crank the windows open here, but it works really well. So with that, we were able to go around and hunt down all of the holes in the walls and stuff, and it was pretty. You can see our tools here is that we use tape. If they're, say, like plywood in general is pretty good as an air barrier, but every once in a while there might be in the different layers of the wood there might be knots or something that are lined up that allow some air to come through. But when you walk by, you can just hear it whistling, and so you can find where that knot is and just put some of the tape over.
Tape. We use tape, caulking, and my favorite. This is my favorite tool. The foam gun. So we used anything we could to plug the holes, and we found there's there's the foam gun. The tape works the best, but there are little holes that even the tape doesn't work. So you actually have to caulk up the. A lot of times, if you have a long break in the CDX plywood, we use CDX. We don't use CCX. We could get away if we use CCX, but it's twice the cost. So the caulking, sometimes you just have to caulk up the whole seam. This one wasn't too bad. The last job, there was a lot more transfer through the plywood. It was surprising the difference in just different factories of wood. So this is one of the details that we worked really hard on trying to figure out how to build a deck. One of the things is the deck is pretty much cantilevered out on one corner, so it's just hanging out there. This is all a steel deck, but the steel is sitting here. It's outside, completely outside of all of our foot membranes. So we hung it. We put a beam in. Did you show the beam? So we built this out here is separate from the building. We built this on the outside of our envelope, and then over here. Does it? I don't. So on here there's a post here. Post base is here, and we took a glue lamp and stood it on end outside of the insulation. So here's the insulation. This is a glue lamp sitting out on the outside. It goes all the way down to the foundation and is tied into the top parapet wall. And that's the post there. And so that whole end of the far end of this steel structure cantilevers out from that post. So the hard part is when you take anything of that size of metal, it's going to just create a huge thermal bridge. So we go through a lot of gyrations with our engineer to figure out how to do it and create to solve the problem with thermal bridging. At our windows, we used the ticks to frame with, which is another thing that we're trying to figure out whether it's actually worth doing or not, because our thoughts were around the windows where we have most of our thermal bridge. Because if you see, we have a piece of wood out here to create our stop around the window on the outside, so we have to put we have to do a frame around the outside window, and then you've got your framing member on the inside. So you'd have a straight through and through piece of wood all the way through the building to the outside. So we put the ticks in, which gives us a thermal bridge here, or a thermal break here, and then this is a piece of XPS, 3/4 inch XPS insulation around the window under our sheetrock. And then we use gaskets around the window, foam around the window, and then we tape on the inside and outside of the window. So there's a layer of tape here and a layer of tape on the inside there. So this is on the ground. This is the framing of one of the ticks, the way we frame a window. This is really typical of so here's our layout of our studs. You can see this is a 4-foot opening, and that's when you frame, you're framing on 4 foot on, you're framing basically 4 foot on center with a stud in between to support the center of the plywood. That's how I see it when we do standard frame is 16 inch on center, so you have more wood in the wall. So we've eliminated about, I think it's about 20 or 30% of the wood just by going to 24 inch on centers. And this one here, instead of a typical framing around a window, typically framing, your sides of your window would have 2 sticks of wood coming up, you'd have a big piece of wood up on top, and then you'd go and put the window sill, and then you'd put a couple of studs underneath that. What we did was we just put a header from on layout stud to on layout stud to bridge that, and then built our window in between. So we took out, I think 1, 2, 3, 4, about 6 or 7 pieces of wood around a typical window, just by doing it the way we're changing the framing, and by then putting ticks in, that even eliminates more wood. So this is our this isn't the same window, but it's kind of the same, isn't it? About the same? Basically the same window. It's these are fiberglass windows. The next project we're using is a, what is that?
Unplasticized PVC.
No idea. Do you want to talk about the windows?
I guess the only thing to mention is that we looked at different glass types depending on the orientation. On the south, you can control the sun pretty well because of overhangs and the angle you get on the south. East and west, that's much more difficult to do because it doesn't matter what time of year the sun gets down lower. You guys have looked at passive solar, but that idea. So the idea is that on the east, west, and north, it made the most sense to have super insulating windows that don't necessarily let in much heat. But on the south side, you want to have obviously good insulation, but you also do want to take advantage of the sun that's down lower in the winter and up higher in the summer. So we selected glass that was different depending on which facade it was. And the U value, I think Energy Star just moved to requiring a 0.3 for the U value, which is basically the lower the number, the more insulating. But the windows we used are as low as 0.13, so they're nearly 3 times as efficient as the Energy Star house would have. I think that's about it for the windows. Okay, so Matt Groves, who's here, he works for the company that manufactured the heat recovery ventilator. Do you You guys have does the idea of a HRV make sense? Okay. Most people haven't really heard of it, so good. But anyway, the product we use is the Zender. There's essentially, in the US market, there's currently two HRVs that work well enough. There's about 30 out there that are worthless, in my opinion. But there's basically two that have been used on passive houses, and we really like the Zender system. One, it's super quiet. When it's running, you essentially don't hear it. And then the other thing that we liked about it is that it's a complete system. It comes with all the ducting and all the diffusers and grills and everything for the whole system. And the ducts are pretty cool because Bart will pass that around. But it's a flexible duct, but it's double layered, so it's flexible, but it's still smooth on the inside. So it's not going to accumulate a lot of the dirt that a typical flex duct would. And it's also 3 inches, so it fits in a standard 2x4 stud. So, you know, we had never done this before the core house, but we put the whole system in took a day or so for the whole unit. So that was pretty cool.
The really cool thing is the way they have their connectors they're just basically an O-ring. So you slide them into an O-ring, and you have a single clip. So
the whole system just snaps together, and it's airtight.
Yeah.
It's pretty cool.
It's like playing with Legos.
The only downside is the product isn't UL listed. So to be able to use it, you have to go through an appeal, but that hasn't been a problem for us so far. So you can see here, this is there's the unit itself, which in our case was in that little bump out on the south of the building. Then we bring in 6-inch ducts that come to, it's a little hard to see here, but you can make out there's this metal box here, and then the 6-inch duct coming from the HRV plugs into those. Yeah, one here and then one here. But then from there, these are the what they call it, the manifold that it breaks down into the 6 ducts that we have that all go home run from here to each room that has a duct. So it's pretty cool. Just the whole thing snaps together, and you don't have to worry about taping or sizing or anything that you have to do with metal ducts. So this is a photo here of the space heater that we selected. The first project we did, the core house, we went with essentially a hairdryer for the house. So I guess I don't have a photo of it, but in the duct for the HRV, we bought a inline duct heater, which is a 1,000-watt electric element that's controlled by the controls for the HRV. That just turns on if extra heat is needed. Great thing about it is it's super cheap. It's $350, so that's your heating system. Downside is its electric resistance, so it's the efficiency is essentially 1-to-1. A passive house uses very little heat, so the idea is that it doesn't really matter that much if your heat source isn't super efficient. But since the goal here was to go to net zero, we decided that really did, if we could make this heating system more efficient, that meant fewer solar panels. So we decided to go with a mini split heat pump. Most common for those is you have the unit that sits on the wall, but we decided that wasn't really the look we were going for, so we chose a concealed version, which has there's short ducts that just duct it basically out of the wall. So all you see is a couple diffusers. But it's the absolute smallest heat pump that's available that we could find. It's rated at 9,000 BTUs, whereas the heat load for the house is something like 4,700 BTUs per hour. So it's still way bigger than what we needed, but it seems to be working pretty well. And then we put a couple electric resistance wall heaters in the bathrooms. One, just for backup if there's an issue with the heat pump, or 2, if you just want to have a little extra heat in the bathrooms. But it seems like so far they're not really using those very much. Then there's the water heating, and that's always a big question, how you're going to heat your water. Definitely spent a lot of time looking at solar hot water. There's a lot of questions about really if it makes sense in this climate here when you look at the cost. Certainly can be argued either way, but we also knew that we're going to need pretty much the whole roof area for PV. So that, and then also the extra weight of the system that would be required for solar. We decided to go with a heat pump water heater. which is pretty new to the market here. But those the byproduct of that is it cools the air. So we decided we put that outside of the thermal envelope. It's located in the workshop in the back of the house. So definitely that's one of the things that you guys are doing monitoring of, and it'll be real interesting to see how that performs over the course of a year. One of the potential synergies is in that workshop. That's also where the inverter for the PV system is installed, and the byproduct of that is heat. So, but it prefers to be cooler. So this is helping keep those cool, and this is the inverters are providing heat for the heat pump water heater. So hopefully there's a little bit of a synergy going on there. Probably the number one most noticeable difference about living in a passive house is actually your dryer. A typical dryer heats up the air and then exhausts it out to the outside. So one, it's a pretty inefficient model that you're just taking conditioned air from the house, heating it up even more, then blowing it out. And that means all the air that's being blown out has to come in from somewhere, so it's sucking in cold air from the outside. But then you also end up with a big duct penetration through your wall that's there, whether or not your dryer's running. And in a passive house, the rest of the building's so tight that if you have a typical dryer that's blowing air to the outside, that air that is usually made up through holes in the wall or whatever can't come from anywhere because you don't have that much leakage in the house. So you'd actually have to open a window to run a dryer, which you obviously don't always want to do. So anyway, what we've done is installed a condensing dryer, which basically heats up the air within the dryer so that water evaporates, and then it runs it across a cool surface and it condenses, and then the water that's in the dryer goes down the drain. And the models that are out now, this is a Bosch from Germany. They're good, but they're slow. I mean, they take, a cycle takes an hour and a half to 2 hours. So the alternative to that is that you put a typical dryer maybe in your garage or something. So that would, yeah.
What's the size of the heater?
Within the, it's a good question. I don't know. I haven't looked into that. We just go off of their rated energy consumption.
Do they cost more?
Yeah, they do. Each, I think they're about $1,000. So they're quite a bit more. But they are, they're German engineering. They're kind of the Mercedes of small washing machines or dryers. But,
The ultimate washing machine.
what's that?
The ultimate washing machine.
The interesting thing is they're all programmable. So like at the core, I don't know if Ella's doing this here, but the courthouse, the owner there has actually decided, she needs the most heat in the morning when she wakes up. So she has it set to run in the morning. She puts her clothes in and then has it turn on in the morning, and that provides enough heat to heat up the house, this degree or two to get it to comfort level. So. And that's exactly what the PHPP is modeling, is it's taking all those internal loads and figuring as long as you can capture them, those will contribute to your heat demand. I think, so just a couple photos. You can see the deck there that we installed. There's two photos here, it's a little confusing. But this is entryway looking back toward the front door. You can see we did a clear kind of glossy finish on the concrete, and there was also a highly finished surface, so kind of a neat effect. And this is looking from that first floor office toward the entryway. You can see the stairs over there, but we made these custom bamboo sliding doors for those rooms. Okay, just back.
Well, this is too far. This is also, you can see how these are the overhang up on top, and the deck. Everything is on the outside of that air envelope. So those were all stuck on after we got our airtight envelope going. So that's an example of how that worked.
This is looking from the top of the stairs toward the south of the building on the second floor. You see, trying to take advantage of the slope of the roof there. And looking back the other direction toward the kitchen. And that's all we've got, but we're happy to answer any questions.
Were you able to cantilever that outside, that with the outside corner?
Hey, Rob, if you could repeat the question.
Repeat the question, sure.
Microphone will pick it up.
Okay. So the question was if we were able to cantilever the deck, because we had the beam on the one corner, if we could cantilever the deck out without a post. And yes, we were able to. We did a moment connection back at that beam. So there's the steel that's coming out from the beam, but then welded to the back of the steel at that post is a channel that runs up and down, and that gave us the moment that we needed. So yes. Any other questions? The back.
You're using a heat pump water heater, right?
Yes.
Are those pretty common? And what's the are you using refrigerant?
So the question was about the heat pump water heater and if they're common and if they use a refrigerant. Again, I'm not a mechanical guy, so I don't know all the details about them. But one question, are they common? No. They've only been around for a couple of years. And really, the model that we use has actually only been around, I think it came out 3 or 4 months before we started construction. And the people, I talked to a number of people like at the Oregon Department of Energy and stuff, that they're doing a lot of testing on heat pump water heaters. And the people I talked to really were impressed with this model. But as far as I know, it's the first installation in Portland of this model. And do they use refrigerant? Yes. I don't know the details on it, but as far as I know, heat pumps all have refrigerant. So because they're transferring the heat through the liquid. But let's see. So yeah. Go ahead.
How much would that heat pump cost and what the recovery rate is?
The cost of the unit itself is about $1,500. So quite a bit more. Electric resistance is what 400? Yeah, $400. In terms of payback, it's a good question. There's so many variables when you're talking about a heat pump.
Well, about the recovery, one of the issues.
Oh, the temperature recovery. Right. Yeah, so the recovery time on them is fairly substantial if it's in heat pump mode. It has controls. You can set it to be on heat pump only, the econ mode, so it only uses the heat pump. Or you can set it to the auto mode, which if it's not able to keep up with demand, it'll turn on electric resistance, which helps with the recovery but also hurts you from efficiency standpoint. Or if you really want to make your meter spin, you just turn it to all electric resistance. What we found so far is it's definitely been a learning experience. We chose, this manufacturer has 2 different size tanks available, a 50-gallon and a 66-gallon. We assumed that 50-gallon would be fine for a 2 or 3 person household. And it seems to be on Ellis and Randy's side. They mostly take showers, and it seems to be fine. And they actually lowered the set temperature to 120. It defaults at 130. They had a tenant move in on the other side who likes to take baths, and they were saying that it's not keeping up with a bath, so we had them turn it back to 130. And I hadn't heard yet how that's working for them. But yeah, there's just an article that came out in greenbuildingadvisor.com, which is just kind of a open forum for a lot of green building issues. And there's just an article that came out about from the editors there about heat pump water heaters, and they were pretty positive about it. They said definitely be careful about where you place it and what your temperatures are.
I think I put a link to that article on the
Okay, yeah. So yeah, they recommended the bigger tank, which we hadn't really considered, but that's so yeah. I'd say for me that's kind of the number one question for the whole building is really how that is going to perform.
As far as the water, did you guys do really tight control of water as well, like using energy control, but
In terms of usage?
using low flow toilets, installation, stuff like that, or not as
So the question was what we did for water efficiency. And I'd say that wasn't the primary focus. We looked at doing things like gray water system, or we did think about plumbing the house for gray water, but it wasn't, just from a budget standpoint, it wasn't something that worked out. We have a 1,500 gallon tank for exterior water reclamation, where rainwater collection. So for all their irrigation, they're using that. And then we have dual flush toilets and low flow shower heads and all that. There's kind of, without going to the next level of doing like recycled water or anything. We did the best we could with that.
Were you able to use your SketchUp model in the actual performance analysis? Did you be able to transfer that information into a different kind of system too?
So the question was if we were able to use the SketchUp model to help with the energy performance. No. I'd say the only thing that the SketchUp was able to do for us is help determine sun angles. You can run through say what your location is and your orientation, and you can see where sun will be and how big you should make your overhangs and things like that. But in terms of, we don't, as far as I know, I don't know of anything that can help take that information and automatically put it into, say, the PHPP or something. If you develop one of those, I'll definitely buy it.
So with the PHPP model, you showed that it was just slightly over-predicting your projected energy use if you assumed that the house used the same energy in the summer as it does in the fall. Right?
Mm-hmm.
So by how much do you think the PHPP ultimately is going to overestimate energy use in the house? It look like you're going to be net regenerative.
Should I repeat your question? Okay, so the question was, going back to that slide about the performance we've seen so far, and assuming that it gets more efficient as we get into warmer weather, it looks like we're going to be the PHPP will have overestimated the amount of energy that's being used by the house. Is that basically your question? You don't want to take.
We first have to put in the caveat of the owner of the building.
Yeah, I mean, occupant behavior is huge. You leave your windows open through the window, and you can just throw out the model. I mean, there's. Fortunately, Ella and Randy are very conscious and make sure to turn off lights, and they pay attention to those things. But in general, the PHPP in the European market has been, if you look at kind of the scatter graph, I mean, it's been pretty good. So far in the United States, it seems to generally underestimate, and it basically comes down to plug loads. I mean, we love our plasma TVs, and people have 5 computers, and the defaults in PHPP aren't currently accounting for that. And that's something that the North American arm of Passivehouse is currently looking at to see if we need to modify those. But then the question is always, well, shouldn't we encourage people to use less? And it's a big discussion outside that. But I think one of the differences is that the numbers from the PHPP are assuming a certain number of occupants, and basically they assume each occupant requires, I think it's 340 square feet or something like that. So Ella and Randy are 2 people, so the numbers are going to come out different. And we can actually go back and I've done that. I've run it with 2 people versus I think it assumes 3.2 occupants or something like that. 3 people in a gerbil or something.
In terms of their personalities and energy use habits compared with Ella and Randy.
I missed the first part of the question.
The tenants.
The tenants.
On the other side now, how would do you know much about them?
No, they moved in. Let's see, it's been a month now. So I've actually never met them or anything. So I have no idea what their lifestyle's like. I know the guys from Italy, so it'd be interesting if that affects it at all. But
Santiago might have the energy data already.
Well, it's actually it's just right now. It's just a. It's
Oh,
just
that's
a
right, it's just
guy.
one person now,
And it's just
yeah.
one person right now because his wife hasn't moved up from California. So they're just one person in there now, and I guess it's next week or something. They're going to both be in occupying.
But yeah, I mean, I think that's, that'll be interesting to see is how that behavioral occupants is affecting those numbers. So.
I have another question. Do you do any sort of economic analysis on the various aspects of what you've done in the passive house compared to what you would normally do? And I mean, which aspect is the most expensive? Which one has the biggest benefit to you? I mean, even rough analysis of that sort.
So the question was about the economics of doing a passive house or doing what we're doing. And there's yes and no. There's definitely the economic side, and really our goal, our ultimate goal would be make it cost neutral. We're not to a point that that's going to happen, and the main reason is the windows. I mean, we're easily spending 2 times, and you could probably spend 3 times as much
We're spending 3 times as much.
on the windows. So that's really where we just get hit. But then the question, the problem that we always have, people ask the question all the time, is how much more is this costing? And it's really hard to say. And one of the big reasons is because passive house, you really have to design a passive house. It's really very difficult to take a house and turn it into a passive house. It's possible, but it's very difficult, and that's the very expensive way of doing it. If you start from the beginning, kind of like we were showing you of keeping our box and simple shapes and all that, the incremental cost becomes much less. But at the same time, people aren't going to design that way if they don't have that in mind. So it's hard to take, yes, we could take the same design and price it as a typical house, but that house isn't going to be, it probably isn't going to happen as a typical house. But anyway, we figure you're looking at about 10% additional construction cost, kind of the last time we took a look at it. That's
the other thing that we're doing is we're not doing a track house. We're doing one at a time. So our economics, the economic of scale doesn't exist. So we're basically doing a low-end custom home. So when you look at those numbers, you're looking at $100 to $120 a square foot per house. We're coming in, I don't know, 140 to 160 a square foot. So if we were to go and say, okay, we have the apples to apples again, then again the same question is, even a track home, they take the same house and place it no matter what their exposure is, where it is. So there's so many different variables. When you start talking about an efficient home, you cannot talk apples to apples. You're still always talking 2 different animals completely. And so that's what it's really hard when people ask me, I'm asked that question all the time. Well, is this like a standard home? I said, you can't make that equation. This isn't a standard home.
So what I hear you saying is that your windows are what make the cost and various different construction methods you're using, with the membranes and the seating and everything else, putting in the concrete floors, all those different things are not that much more expensive than if you were to build a standard method.
Right.
it's mostly thinking about things beforehand and not just doing them what's typically
and
done.
plus I have an architect on staff and a certified passive house consultant. So those are costs that we would have to pay, and we've had to pay for. So we have those in-house. So those are some of the costs that if you were to go say to any other builder out there, build me a house, you're going to spend the money to have the house designed, and that's where the hardest part of this whole thing is. We're building it for ourselves to sell, so we can absorb some of those costs in the beginning, and then we hopefully our per square foot sale price will change that.
But I think the economics are definitely a big factor in it. And again, our goal is to do this really as affordably as we can. But then there's also just a lot of kind of the side effects of building this way that don't have anything to do with energy consumption that for us turn into big sales point. one is the air quality. Because of the HRV that's running 24 hours a day, we're providing a much higher level of air quality than a typical house would, where most of your ventilation is just coming randomly, basically, through the infiltration in your house. So that's one. Another thing is because we have so much insulation and these triple glazed windows and the air sealing and everything we do, these houses are silent. Which, depending on your location, like the first house we did was a couple blocks from the freeway. You close the doors and you could be underground. I mean, it's silent, which for a lot of people is a big selling point. And then just the comfort level. You don't have cold spots by the window because, I mean, you're performing as well as a lot of walls with this glass. You don't have a big temperature variation from top to bottom because the air is constantly being moved, and you don't have the infiltration that you normally do, and so they really just are much more comfortable to be in as well. And then just from we're building a house that we hope is around in 100 years, and so to me it doesn't make sense to build for right now. We should be looking at trying our best to think about what the situation will be in the future, and not just almost selfishly for what we'd be wanting, but also just for the planet and for energy consumption, and so I think there's so many factors that kind of go beyond the economics of it. At least for me. I mean, it's not for everybody. But
so, are you on to your next Passive House project yet?
Question is if we're on to the next one, and yes, we're about to submit for permit. It's been a slow process because we have to go through a big, long process with design review and everything on this project. But the next project is another 2-unit kind of townhouse-style project. But this one will be a spec project, and we're hoping to do net zero again. So that could be pretty cool.
Where generally is it?
It's in Northeast, just off of Burnside, 72nd. So
It's not the other.
yeah, it's not very.
Do you have any concerns with that heat pump water heater dumping all that cold exhaust into the back corner of your house?
The question was if we're concerned about the cold air coming off of the heat pump water heater. I guess concerned is probably not the right word. It's not it's outside of our envelope. I don't think it'll affect the performance of the house. It's making that room really cold. And that's definitely, I think for some people that would be a real problem. For other people, you just figure that's essentially outside, rain protected and weather protected, but not temperature protected. So, I think Ella's still trying to figure out if that's a issue for her or not. I think we have heard a few things, a couple comments about it being really cold in there, and it is. I mean, it's in the winter. It's 40, 45 degrees in there. But that's just. I think I'd say if you're looking at installing one, I would definitely make sure the person who's going to be living with it knows the ramifications. It'd be awesome if we could figure out a good way to integrate it on the inside of the unit, so that in the summer we could take advantage of the cold air, and in the winter, if we could duct in the air from the outside or something, so that you're not affecting the space. But they are also pretty loud. Right now, you don't hear it because we've got a 13-inch wall between you and that. But that's one thing to consider if it's inside your envelope. So, in the back.
Of the two passive houses that you guys have done, I mean, you showed in the PHPP that it met certification criteria.
Mm-hmm.
But is there an actual certification process, and have these houses, the two that you guys have done, have they been actually certified?
So the question was about Passive House certification. The first house, the core house, is certified. The Trekhaus, we're going through certification right now. And basically they've come back and said we had a few modifications that had to be made. But now we're at a point that the whole model and everything looks good. The problem that we're having is getting the blower door test certified. they now want, it used to be that you could use essentially anybody that knows how to use a blower door. Now they want you to use someone who's specifically Passive House trained. And there wasn't, until a couple weeks ago, there wasn't anybody in Portland. But we don't really want to redo the test because that means going into the tenant side and checking all their windows and doing all the things that you have to do to get ready. And so we're hoping that they'll accept the ones that have been done, but we just haven't been able to work that out. But we hope to be certified pretty soon. But the certification does come it's 100% off of the modeling. They want to know about the performance in the future, like to check it against the modeling, but it's not something that they won't revoke it if you come in over. So, I think there's a question here.
Did you guys get any incentives from the Energy Trust on any aspect of this? And if you want to share, what was your profit margin?
Let's see. Question was Energy Trust incentives and profit on the construction. Let's see. There's a number of incentives that we got. Let's see. Energy Trust has a sliding scale depending on, they have their own modeling system. And the better score you get, the more money you get. We maxed that out, which was $4,000 per unit. Then they also had another incentive that is called Solar Ready. They basically want you to get the house ready for solar, have the conduits in place and a place for an inverter and all that. And so we got that. That's a couple $100. And then there's, it no longer exists, but there's the business energy, Oregon business energy tax credit. We squeaked in for one of the units, for the rental unit. There's a $7,000 tax credit that we could get for, if it's not owner occupied. So we'll get that for one unit. And then for the owner occupied, there's a number of kind of smaller credits. For the water heater, you can get a credit. For the windows, you can get a credit. For the, they have one for solar, passive solar. So that's $1,500. So I think she ended up getting $3,500 or so in credits there. There used to be, until this last year, there was a federal credit of $2,000. But that's profit.
You saw the picture of Bart with bow tie on it.
Yeah, that was.
It's pre-funeral. Mine.
We've been doing fine on these. The big factor now has been our learning experience. We're taking way more time on these than would typically be taken, and we're not necessarily charging that to the client because we want to get better at this and continue to do it. And if we're going to charge those true costs to our client, then that wouldn't get built. The learning curve. I think in my mind it's the only way to go, especially in this economy. I think people are looking for cheap. There's foreclosures and there's short sales and everything. They look for cheap, or they're looking for something really different and special and better. For the first, we weren't trying to sell this project, but for the first one, I was trying to sell the house in 2010. Never even put it on the market. Put a sign out front, had a website, and that was it. And ended up with multiple offers, and we probably could have sold that house a couple times over. And we sold it at the asking price. So.
Being a builder in the first place is a losing proposition. But in the long run, what it really comes down to is you have, I've probably built 50 houses on my own. I do it the same way we're doing it now. I just build them one at a time and sell them. I've done very well, and I've done extremely bad. And so the one thing that's different about this is I've thrown out what's the market going to want? And I've decided to build with Rob what we want and what looks good to us. And the reason I've done that is in the past I've talked to a lot of builders, and that's the guys who are actually making a difference and making money are the guys who just don't care. and throw out the whole model of I'm going to make this vanilla house that everybody wants. That doesn't work because nobody will want it. The only houses people want are the ones that they can say, hey, that's my house, and it's the only one like it. And that's what houses sell well. So this is what a lot of people want, is a house that is highly efficient home. I mean, there's hundreds of houses out there that right now you can buy that don't perform well. They're the same old thing. They don't have any ecological or social meaning to them at all. They're just a house. So what we're trying to do is build a house that has economic, ecological, and social meaning to it, and that seems to be a very good place. We haven't been hurt yet. We have made money on each one of these homes. It hasn't been a great amount of money, but right now there's not a lot of builders out there that can say they made money on homes. So, yeah.
I was just curious, you mentioned the value of these projects as a case study for future projects, and especially to get background in modeling. I'm sure you had some familiar with the Trekhaus developments that go up very quickly. Considering how many of those are out there now, how quality of do you using these experiences to be able to scale up, to apply these things more affordably with that scale, but also I think there's a lot of importance in doing refurbs or things on existing really poorly performing houses that are out there. For instance, I live in Vancouver, and so it's just a wasteland in some places. There's just there's no concern. I mean, simple things like orientation or just some simple procedures. I would think there's a huge future market out there for that.
Yeah. So the question is there a market for the tract home, the quick track home building, and also retrofit? There right now, I've done two estimates on doing a retrofit. It costs more to retrofit a house than it is to tear it down, start over. And then you've got orientation and stuff like that. So one of the things they're trying to do in Passivehouse, if I'm right, is they're trying to do a retrofit passive house, and it's a lower standards. And I have a couple ideas and bouncing around my head that would make retrofitting faster and simpler. The hardest part is you're taking an inferior wall and you're trying to, basically turn it. It's like taking an 80-year-old guy and trying to turn him into a bodybuilder. You can be done. It's going to take a lot of work, and it's not going to look pretty. So the thing is there is, and that's the thing my heart bleeds about it, is the fact that to really make a dent in the carbon emissions from homes and the carbon footprint of homes going forward, you're going to have to address the retrofit issue. There's just too many out there that are just sucking gas and blowing carbon, and so the only way to do it is to actually come up with that. But we're on the bleeding edge as it is with new construction. It's going to be an even deeper cut when you start trying to do the. So if we can find a manufacturer in the U.S. that'll produce a window that will work, that's inexpensive enough that we can use them in retrofits. If we can find a way to attach insulation and siding to the outside of a building on a retrofit, and a way to airtight those buildings, then we're starting to talk about some things that we can do. And yeah, Rob and I talk about that probably on a weekly basis, but it's very difficult. It would be. I mean, really, we're
There's no reason that they should be that expensive. They're not that. It's not rocket science.
Yeah, there's hundreds of people out there that can make these windows. It's just that there's just not a demand here in the U.S. for windows on steroids.
Maybe one or two last questions. And we'll
Okay. Santiago.
Do you see any benefit to perhaps going towards passive prefabricated homes? Do you think there's a possibility of actually making that work on a less expensive scale?
The question is pre-manufactured passive homes, and a couple of things stand in your way. Yes, it can be done. One, then you move into problems of shipping and site built. And your insurance companies and your insurance industry is going to shoot you in the foot every time you try to do a non-site built house, period. Your insurers go up, they just don't like them. And so there's a whole industry that you've got to overcome. Cost-wise, you could probably do it. Again, it has to be, that has to go to high scale, and I'd like to see it. And then, I don't know his name, but he's been itching to say something.
I just want to know if the windows are argon-filled and if they've been leaked and you've had to replace them.
Are the windows argon-filled and how we have to replace them?
I forget if it's argon or.
They are.
Okay, so they.
So yes, they do have a gas, and we have not had to. Well, I mean, we've had to put in new. We had some break and stuff.
Okay.
But we haven't had that problem yet with the gases leaking out. It will happen. I mean.
Yeah, some kid's gonna throw a ball.
Well, even just the seal over time, it's not going to hold up forever.
Yeah.
What I've seen is that even though the performance does at some point reduce, probably 25 years or so, is that the energy you save up to that point are enough to offset the cost. It's not that expensive to put a gas in a window. So from what you could argue that it doesn't make sense because in 100 years it's not going to be performing at the same level.
But you've never had any like DOA? Like,
No.
Well, the first windows we put in didn't have gas in them. The first windows were a 4-pane. 2 of the panes were a suspended cellophane. So they don't have those. The cellophane replaced the equivalent of the gases. So there were no gases. In fact, those came from back east, came over the Rockies, and they came with air tubes in them. The ones we just put in had to go from Ontario down to Texas, over to California and up, because they couldn't go over the mountains because they were pressure windows. So those are just strange little things you find out. So I guess that's it.
Thank you so much.
You're welcome.